Welcome, everyone. I just wanted to talk a few minutes about the final project and especially how to match the C3 at Flyby. So why do we want to do that in the first place? Well, it's because if we take a look at what happens at Flyby, we're entering the sphere of influence of Jupiter with a certain V infinity. And since nothing happens in terms of thrust or any other force that changes the energy of the spacecraft with respect to Jupiter, we're going to leave the sphere of influence of Jupiter with the same V infinity in terms of magnitude. Of course, the direction is different, but the magnitude of the velocity is the same. And you know that C3 is V infinity squared, therefore the V infinity at the entrance of the sphere of influence has to be the same as the C3 at the exit of the sphere of influence at Jupiter. With that being said, we should start generating the Porkchop plots for the first leg of the journey, that is from Earth to Jupiter. So here, looking at the suggested times, we can choose before and after the ideal launch date, minus and plus 50 days. And if you want a pretty precise Porkchop plot, you can just keep the increment to 1 day, whereas for the time of flight, again, this is always from Earth to Jupiter, we can choose 400 to 1500, and you can leave it at 10 or you can reduce it later on. We're just gonna leave it at 10 because it's still gonna take a little bit to generate the Porkchop plot. Now, what date is going to be our ideal launch date? Technically, you can put any date here. It doesn't really matter. This is just to center the x-axis. We saw that normally we prefer as our ideal launch date the date at which we have the perfect alignment for a potential Hohmann transfer. Know that the Hohmann transfer cannot really happen because the orbits of the two planets do not lie on the same orbital plane. However, we're still going to use that ideal launch date as our potential Hohmann transfer. So given the fact that for this project, the time window, the possible time window for the launch is between June 2029 and June 2033, we really only have 4 dates that we can look at. So you should repeat the procedure that we're seeing right now 4 times in 2030, 31, 32, and 33. So let's focus on the 2030 ideal launch date. So we're just going to insert the date. So it's 2030, January 27th. So here it's going to take a little bit. And of course, the computational time depends on the power of your CPU. So I suggest for the Porkchop plot generation to use the most powerful computer that you have at your disposal. However, once you generate the Porkchop plots once, that's about it. So you don't really have to generate them over and over again. Not necessarily, not if you follow these instructions. Okay, we're almost done grilling here. Okay, so we have our 2 plots. Why do we have 2? Well, one refers to the C3 levels at departure, that is the V infinity squared at the exit of Earth's sphere of influence, whereas on the right-hand side, we have the C3 levels, that is the V infinity squared at the entrance of Jupiter's sphere of influence. So see that the only levels on the left that I'm visualizing are the ones below the 130 mark. So why is that? Because 130 is the capability, the maximum capability of our SLS. So all the points outside this contour, this black contour line, are irrelevant, cannot be obtained with our launcher. So it makes sense to replicate this contour on the right-hand side because all the points within the black contour line will correspond to the possible C3 at arrival to Jupiter. Okay, so what are the possible C3s at arrival at Jupiter, at the entrance of the sphere of influence? Let's see. We have to follow the lines, so we see that here we have 55, 50, 45. We're looking for the maximum value. So following this contour, we see that the maximum is going to be around here. We can zoom in, and we're looking for a maximum C3 of about 250. So right now, record this value. So you're going to have a C3, maximum C3 at Jupiter of 250 kilometers squared over second squared. One thing that you could do now is to take a screenshot of this Porkchop plot, which I've previously done that, because then we'll need to compare the right-hand side of this Porkchop plot pair to the left-hand side of the new Porkchop plot pair. One more thing here, this straight lines that are slightly diagonal and dashed, they indicate the amount of days after the 0, that is our ideal launch date, ILD. Before going to the other Porkchop plots, let's take a look at the limits in terms of the time of flight between Earth and Jupiter. So the minimum amount of flight corresponds to this point over here. So it's about 450 days. You don't have to be super precise here. You can just look at these plots. And then the maximum amount of time, it exceeds, clearly here, it exceeds 1500 days. We don't have to go for that. We can just cut off at 1500. That's going to be fine. More than that, it's really not going to be viable. So the range of time of flights between Earth and Jupiter will be between 450 and let's say 1550. Okay. So now what we're going to do, we're going to change our parameters here for the generation of the Porkchop plots. So first of all, you want to change your planets. So now your planet number 1 is Jupiter, because we're looking at the second leg of the flight. And the second planet is Neptune. All right, so what about our launch days? We'll still consider the ideal launch date as we found earlier, that is January 27th, 2030. And here the minimum amount of days is going to be the lower bound in terms of the time of flight between Earth and Jupiter. So we said that that was 450. And the maximum can go nuts here, but let's limit ourselves to 1550. And here I don't want a super precise grid, otherwise it's going to take forever. You can just keep the interval, the increment to 50 days. And then time of flight here. We know something about the maximum time of flight because we have a requirement in terms of how long our mission should be. So our mission can last at most 15 years. So we have 15 times 365 days, but we have to subtract the time of flight between Earth and Jupiter. Now, we don't really know what that one is, because it can be anywhere between 450 and 1550. So let's just subtract the minimum. So 450. And what about the minimum time of flight between Jupiter and Neptune? Well, you can try different values here. I'll just go with 2000. So 2000 is approximately 6 years, which is it's pretty fast, but it's not going to take you less than that. So you can keep this, and we'll have an increment of 50 days here as well. What about the maximum C3 capability? Now, the C3 capability here is a fictitious C3 capability. It doesn't really refer to the capability of a rocket. We've already consumed all the fuel in our rocket. Now we're just flying. So here you should really put the maximum C3 that you are expecting at flyby. And that was the value that I told you to record earlier. If you remember, that was 250 kilometers squared per second squared. So let's check everything. Jupiter, Neptune. All right. Launch dates, time of flight, and maximum C3 capability. So now we'll run the code, and we'll open this horizon. You can just close this. And for the ideal launch date, just put the original one. So it was 2030, January 27th. And we'll just wait for the Porkchop plots to be generated. You see that even with a quite generous increment of days, 50 days between two successive points, it still takes a good amount of time to generate the Porkchop plots. So if you're not sure that you're actually nailing the Porkchop plots in terms of the right amount of time of flight, relax the time of flight increment or the launch date increment, and then you can always make it stricter later on. You don't want to wait 5 minutes every time. So I tried this before, and I know these are good intervals. So I can choose a quite strict grid if I wanted, but this is, as you will see, this is going to be good enough. Still a few more seconds. All right, here we go. So now to the left, we have all the C3 levels. Now it says at departure from where? From Jupiter. Where are you departing Jupiter? Well, that corresponds to the exit of the sphere of influence. And see that all the values are limited, are confined within the 250 mark in terms of the C3. Anything more than that would not be feasible. And then to the right, of course, we're going to have the C3 at arrival. Now, my suggestion that if you can keep this plot here or take a screenshot of the left-hand side of the plot so that we can compare the C3s. So let me just show you how to find a feasible solution, just one feasible solution, at least in terms of transfer between Earth and Neptune. So that would satisfy the requirement of the initial C3 below 130 and the total time of flight. Then the other requirements, well, you'll have to check them. So we're going to move this to the right, and we're going to resuscitate here the right-hand side of the previous Porkchop plot. So you see here, this is the arrival at Jupiter, and this is the departure at Jupiter. So how do we find a common C3? Well, we can start, for instance, we start from the left-hand side, and let's say that we're following a line corresponding to plus 10 days from the ideal launch date. We follow it vertically until we meet whatever contour plot that you want. So let's say that we want to stop at 50. So 50 means that the C3 at Flyby is 50. So this corresponds to a time of flight of about 760 days. All right, so mark that down. You have plus 10 days with respect to the 27th of January 2030. It's going to take you 760 days, roughly, to get to Jupiter, and you'll get there with the C3 of 50 kilometers squared per second squared. Now let's move to the Porkchop plot relative to the departure from Jupiter's sphere of influence. So we're going to go to the x-axis and find the same time of flight that was 760 days plus the 10. So we're looking at 770 days. So 720, 40, 60. So we're about here, and we want to go up vertically until we match the C3. So until we intersect the 50 line. So again, here we can do it slightly roughly. We don't have to be super precise. We'll have a tool to match exactly. So here we just want to have an idea of how much time it'll require to go from Jupiter to Neptune. So at 50, at around 770, we have a time of flight that is around here. So this is what? Between, it's about, 4140, let's say. It's a little bit lower than that. So write that down. Time of flight between Jupiter and Neptune predicted is about 4140. Okay, so we have a rough idea of the two legs of our journey, but now we can compute them more precisely using the other piece of code, the interplanetary transfer. So let's go with the first leg. We start from Earth and we want to get to Jupiter. So we're launching, the ideal launch date is 2030, January 27th. Then we have to add that additional day because we were looking along the plus 10 line. So that's where you need to add that 10. And we said, okay, we were looking at about 760 days. So we're expecting that with these values, we're going to find a C3. We should find a C3 at the arrival to Jupiter that is roughly 50. So we'll run this. So of course it shows you here the launch date, the arrival date, time of flight 760 days. But in the command window, this is where you want to pay attention to. And there you go. Look, at arrival at Jupiter, our C3 is 49.3 kilometers squared per second squared. So very close to the 50 that we predicted. So what you should do is to copy this information, especially the V infinity as a vector, but also everything else. Why not? And then we go to the second leg of our journey. So we have to go from Jupiter to Neptune. Again, it's much easier if there is more than one of you doing this. So one can focus on the first leg and another person on the second leg, and the third person can check the fuel consumption later or the flyby condition. So that's why you're a team, right? All right, so we ideal launch date always 27th of January 2030. We already added the 10 days because that's where we actually depart from Earth, and we need that's 760 days to get to Jupiter. Then from Jupiter to get to Neptune, we predicted from the Porkchop plot that it's going to take us about, what was it, 4,140 days. Now, is it going to be exactly this? Most likely not. So if we run this simulation, we'll see that now we have to look at the C3 at departure from Jupiter. That is when our spacecraft is leaving the sphere of influence. Right? Now we're looking at this vector. So we're still looking at the same magnitude. We know that we had 49.3, so we have to match the 49.3. Let's see. Have we matched that? Very close. It's 49.2. So let's change it a little bit. Maybe let's decrease this by a couple of days. Oh, there we go. So very, very lucky. And so the total time that it will take you to go from Earth to Neptune is the 760 days. That was the initial time of flight, plus this 4,138 days. And overall, you're still within the requirement of 15 years because the second leg of the flight is 11.3 years, whereas 760 days is slightly more than 2 years. So you're well within the requirements. Moreover, you can also find the exact C3 at departure. You should have read that before, and I apologize for that. So let's recreate what we had before, the first leg from Earth to Jupiter. Now this 760 goes here. Just to make sure, for peace of mind, that the C3 at departure is indeed within the requirements. Yes, it is 97.4. So you know that it's 97.4. Now what you can do is go to the useful payload system mass versus characteristic energy. This is the plot for the SLS. And or actually you should be using the function that I asked you to develop. So for a 97 point something C3, you'll find exactly how much mass you can deliver at the boundary of Earth's sphere of influence. So it's going to be about 6 tons or so, between 5 and 6 tons, I assume. But that's why if you have that function that interpolates this data, you'll find exactly how much mass you can fly from Earth to Neptune. Of course, at Jupiter, you don't have to expend any fuel, so the mass remains constant. The mass that you've launched and you've accelerated at the boundary of the Earth's sphere of influence is the same mass that will arrive at the boundary of Neptune's sphere of influence. So then you can, based on the mass that you have, you can compute the delta V capability and compare that delta V based on your C3 of arrival, your V infinity at arrival at Neptune. You can compare that with your delta V capability. Oh, sorry, you can compare your delta V capability with the delta V that is required for the insertion in your capture orbit. So that is one thing to do. So this overall trajectory is feasible physically, but it might not be feasible with the amount of fuel that you have. Moreover, you have to verify that things are actually possible at Flyby. What you have with the two legs are the v infinities. So here at Jupiter, you have the vector, the v infinity at the entrance of the sphere of influence. And once you compute the second leg, you have the vector with its three components at the exit. Now, you have two vectors, so you can easily calculate the angle between these two vectors, and the angle between the two velocity, the two v infinities at the entrance, at the exit of the sphere of influence corresponds to the turn angle. So you have the turn angle, you can retrieve the direction of periapsis. From the direction of periapsis, you can retrieve the eccentricity of the hyperbolic orbit, and then you can combine this formula that gives you the hyperbolic excess speed and the orbit equation at periapsis. You combine these two, and so you have two unknowns, two equations into unknowns, the unknowns being h and rp. So you can explicit h from one and then substitute it in the other, find rp, compare rp, which is the radius of periapsis at Jupiter, at Flyby, compare it to the radius of the planet. If the former is greater than the latter, it means that your altitude is positive, and therefore the flyby is feasible. So you see that we can do pointwise a search for a feasible trajectory. Now the challenge is to optimize this search so you can do more than one at a time. And also don't forget that you have other years, so this whole process should technically be repeated for the years 20, 31, 32, and 33, possibly. And then come up with a bunch of possible trajectories, and ideally you would have to choose the best. So you'd have to justify why that trajectory that you choose is the best, and best depending on which criterion. I'd suggest to use either the minimum amount of flight, overall flight, between Earth and Neptune, or you can choose the trajectory so that you'll arrive at Neptune with the most amount of fuel. And so you will have the capability of doing additional maneuvers and extend your mission to somewhere else. So yeah, that's all. I wanted to cover this, and good luck.